Alright, this is the fifth video for Module 12, Electromagnetic Force. We've talked a lot about electricity, electrical circuits, electric current. Today we're going to talk about the other half of the electromagnetic force, which is magnetism. Alright, so magnets, something that we've all very familiar with. We've been playing with magnets since we were little. We've been using magnets to get things done. What you may not realize, though, is that magnet and magnetic forces are a result of charged particles. So charged particles are going to be your protons and your electrons in your atoms. When they move, not only do they have an electric field, they also have a magnetic field. They are related. They are one and the same. So every charged particle is making an electric field and a magnetic field. And since electrons are all moving all the time, all of them are going to have a magnetic field and an electric field around them. Now what's interesting though is that each of these little atoms, which they are magnets in themselves because they have a magnetic field, are not necessarily very strong. So in order for a material, so like say a pencil or a nail or anything else, in order for them to become magnetic, those atoms, which are little magnets themselves, have to be lined up so that the electrons have the same motion, so that the electrons are pulling in the same way. So most of the time in each of your, like say your pencil, you've got one little atom that's facing this way and one that's facing that way, and they're just facing all, it's very random and crazy and disorderly. All right. So in order for an object to become a magnet, like say a magnet that you would use on your refrigerator, you have to get them all facing and working the same direction. Right? So that's what it takes for things to become a magnet. Now there are some things that normally aren't magnets that can be made into magnets. And then there are some materials that it's never going to happen that way. Like a piece of rubber is never going to become magnetized. Now just like in electrical charges, like poles repel, which you should already know that, we've played with that before. You know you have two north poles when they push against each other, and opposite poles are going to attract. Now magnets are very special in that they are dipoles. So if you have a north pole, you have to have a south pole. You can't ever just have a north pole or just have a south pole. They only come in pairs. Okay, just like forces, they only come in pairs. So no such thing as a magnetic monopole. If you took a magnet and you cut it in half 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 and you got it down all the way down to the little atom, you would still have a dipole. There's always going to be a north and a south. So no matter how many times you break it in half, you're going to have two poles, a north and a south. If you take a magnet and you break it in half, now instead of having two poles, you have two norths and two souths, because now you have two separate magnets. You can do this as many times as you like, but you'll never get a monopole. Right. Now, you can have a magnet that you can make stronger by getting more of the atoms aligned. So let's say we had a magnet and they were almost all aligned. We kind of had that one sticking off over there and maybe that one sticking off over there. Okay, so if you take this weak magnet, because some of them are lined up, and you were able to jostle those around and get them to all line up, now you can make it a stronger magnet. Now the interesting thing is just like electrical force and gravitational force, your force of the attraction between your poles is proportional to their strength. So if you want a north pole and a south pole to be even strongly attracted to each other, you got to increase the strength of the pole. You increase the strength of the pole by aligning more atoms. And then it's indirectly proportional to the distance between the poles. So if you take two magnets and you move them far apart, they're going to have less pull on it. So if you've ever taken a magnet and you have one on top of your hand and one underneath your hand and they're able to stick together and it looks like you're magic, you've got them floating there, the further apart they are, the less attractive they are to each other. So if you were to take it and you had one on the top of the table and one on the bottom of the table and they're attracted to one another through the table, if you were to get a thicker table, then the further apart they are, the less force or attraction is between your two poles. Now we can draw pictures of what this force looks like by using magnetic field lines. Okay, these are magnetic field lines, are just going to be pictures of how strong the force is between the poles. Right, so this would be an example of magnetic field lines. So you can see that there's a bar magnet in the middle. You've got a north pole and a south pole. And if you take iron shavings and you sprinkle them around your magnet, this is how they will separate out in. This is what we know what field lines look like. So if we were going to just draw these field lines, this is what we would do. We would have our north pole and our south pole on our bar magnet. Now on a bar magnet, your ones on your ends are going to come straight out. If we were to extend this picture, you can see that they actually just keep making bigger and bigger circles. Okay, so the ends, they go out, and then from the sides they're going to go, because this north pole is attracted to the south pole, and so that's where the forces are going. Now the stronger the magnet, the closer your field lines are going to be together. If it's a very weak magnet, let's say we had this little bar right here and he's very weak, then maybe our lines are really far apart. Okay, and then if we had one right here and let's say he was really strong, we might have lines that look more like this, where there's a bunch of them and they're really close together. So how close they are together tells you how strong it is. And the one in this picture right here looks like it's pretty strong. There's homework tonight. Go ahead and click on the link, finish the quiz, and I'll see you in class.